So our aim is to get equations that shows us how eta, the catalyst effectiveness factor, varies with our Thiele modulus for higher order reactions. For first order reactions, we know we've got this equation that applies over the entire regime set. So whether I am here where it's eta is 1, reaction rate limited, or where eta becomes inversely proportional to the rate, doesn't matter. This equation will apply over that entire sequence of Thiele values. For any other order reaction, the problem is that we actually need to know in which regime we are before we start modeling. In other words, we need to know, am I in the regime where I can use eta is equal to 1? Or am I in a regime where I can assume that I've got internal diffusion limitations to such an extreme that eta becomes inversely proportional to the Thiele modulus, where I have equations. But for higher order reactions, we've got this regime of uncertainty, where I actually do not know or don't have analytical equations for eta available. So the problem is that if you have rate data and you want to model, you want to find out what is the value of K dash, what is the value of the rate order, you actually need to know where you are before you can start modeling this. So you are not in a position to calculate a Thiele modulus for these higher order reactions. In order to solve that and to determine in which regime you are, researchers came up with this parameter, the Weiss-Prater parameter. It was probably somebody Weiss and somebody Prater, where you can use your measured rate data to figure out which regime you are in. So for batch data, of course, this rate will change with each reaction step, but you will know what that value is for each timestamp. And in a CSTR, you will be able to find that measured parameter from your mole balance. You then calculate the particle rate using that measured particle rate and correct for the units and divide it by the same diffusion rate, effective diffusion rate in your particle. So Weiss-Prater parameter, crucial that you are able to calculate that to determine in which regime you are for higher order reactions. So now, if the Weiss-Prater regime is less than 0.1, regardless of the rate order, first order, second order, fifth order, whatever order rate you have, you know that you are in the reaction rate controlled regime and eta is equal to 1. If your Weiss-Prater parameter is larger than 50, regardless of the shape of your rate equation that you are going to find, you know that you are in the regime where your rate is severely limited by internal diffusion effects and you are actually in a range where it's an inverse proportional linear relationship. And in that range, we have equations where we can describe eta as a function of the Thiele modulus. So once we've proven that we are actually in the internal diffusion limited regime, so we now know our Weiss-Prater parameter is higher than 50. An equation is available, you don't need to be able to derive it, for eta for higher order reactions as a function of the Thiele modulus. What is important for you to realize that if you are in this regime, eta is inversely proportional to the Thiele modulus. Note, for first order reactions, I can also apply this equation. This becomes equal to 1, this first part of the term. And similar to when we applied our Koch equation for eta reaction order 1, we can prove that in that regime, eta is equal to 3 over Thiele. Of course, for first order reactions, we also know that that occurs when the Thiele modulus is higher than 20. So what this information allows us to do is to actually realize what is the proportionalities that governs the shape of our eta value, our catalyst particle effectiveness factor. Because we know how the Thiele modulus depends on these parameters, directly proportional to square root Ki dash. Of course, this implies a strong temperature dependence. The particle diameter directly proportional to that, and of course for higher order reactions also proportional to my concentration of reactants at the surface of my catalyst particle. We can now see that our effectiveness factor will become smaller as I increase the particle diameter. It will become smaller as I increase my temperature, and I know exactly in which way it will become smaller because I've got this proportionality. So we now apply this to our particle volume-based rate equation. So this is the start. We multiply by the catalyst particle density in order to get this per cubic meter catalyst particles. Substitute this equation for eta in that regime. Remember, in the Weisbrater higher than 50 regime. Also incorporate, of course, the Theme modulus, and the equation that results are shown here. It may be necessary for you to pause to make sure that you agree with the equation that I typed here. So after you've proven that you could derive that equation, or derive that you get to that equation by substitution of the eta equation, divide again by our catalyst density. Why? Because we want the rate per kilogram catalyst. We want the mass-based rate that we can apply in our reactor. So now spare a moment to look at this equation. We've got stuff that is in front of my concentration. It looks like a form of a K value, a rate constant, and we do have a reaction rate order, which is not the true rate order that I would get if I were free from any mass transfer effects. So here I retype that equation that we derived in the regime where eta inversely proportional to the Thiem modulus, except in this case I've shown the full expansion of the intrinsic rate constant and its contribution to that rate expression to highlight the fact that we also include the pre-exponential constant and the Arrhenius temperature dependence in that modified rate equation. If we inspect that rate equation, we can see that it can also be given as a rate that has a rate constant as well as an apparent rate order in it. So this is what you will measure if you do experiments and you are in the regime where internal diffusion limits the reaction rate. So if we inspect the temperature dependence of that apparent rate constant, we can see that there are two variables that can affect the rate and have a variation in temperature. Effective diffusivity, the variation so small that we are going to assume it to be negligible. We are going to consider the effective diffusivity to be a constant in all our analysis. But we need to incorporate the effect, the Arrhenius temperature effect of our true intrinsic rate constant. Just remembering that now it is held back by this square root of that term in our rate equation. So if we now should rewrite it, we can say that my apparent rate constant now concerns, it has a term that's got a pre-exponential constant. What I must now remember is that all these terms now forms part of that pre-exponential constant. So it's not a constant anymore. It's going to vary if I change the particle diameter and if I change the catalyst density. In all our problems, what will happen is that I am going to change the catalyst particle diameter, and therefore the apparent pre-exponential constant will change if I am in the mass transfer limited regime. Also important to note is that the apparent activation energy that I will measure, if I increase temperature and I have subsequent experiments, that slope with the increase in temperature is not going to be so significant. In fact, it is going to be exactly half of the true potential activation energy of that reaction. That is because the rate is held back by the relative temperature independence of the diffusional rate process. My reaction order, if you inspect that equation, will still be first order if I have a first order reaction. That's because both the intrinsic reaction rate and the diffusional process are first order dependent, concentration dependent processes. For higher order reactions, that order will be apparent because it is affected by how sensitive the diffusional process is to the concentration, and that is always a first order process.